right, so let's have some fun before lunch with a somewhat lighter topic, Web WebAssembly. So my name is Steven. I'm a lecturer at the Hoogland University of Applied Sciences in Belgium. So unlike most of you, I'm not an iOS developer. I'm not even a developer. But I do try to contribute to open source when I can find the time. I've done some of the initial work on the Swift extension for VS Code, which I'm going to be using in the demos. I've worked on Highlight.js, the Swift support for Highlight.js, which you may be familiar with since it powers the Swift UI tutorials, and some various other stuff. But most of my free time, when I'm not teaching, I spend building this platform, which I call the PWS Academy. It just stands for Programming with Swift, because I had no inspiration. That's where I collect all of the work I do with Swift in education, which is my primary focus. So what I'm trying to do here is I'm trying to build out a platform with hopefully high-quality courses that are freely available in case anyone doesn't have access to affordable higher education. But of course, since I'm a big fan of Swift, I'm also trying to promote Swift as a teaching language in higher education to replace the Java and Python and so on that we're using today. I think Swift really has a lot of features that make it really suitable as a teaching language, but it's lacking a bit in cross-platform support. But nonetheless, I'm moving forward. So we have one course online, which is quite unique in that it's a Programming 101 type course, but it uses Swift, and it fully supports Windows, especially Windows and Linux, as well as macOS. So ever since Swift was open source, I've been closely following all of the efforts being done to port Swift to new platforms, open up new use cases, and so on. And this talk is about one of those projects, which is SwiftWasm. So SwiftWasm stands for Swift WebAssembly. This is a project that enables WebAssembly support for Swift. So I've spent about a year digging into WebAssembly and SwiftWasm, and this talk is a little bit of a summary of what I learned and hopefully teach you some things about WebAssembly and what it can mean for you as a Swift or iOS developer. So what is WebAssembly? Well, spoiler alert, it's not assembly for web. The name is a bit misleading. It describes itself as a binary instruction format for a stack-based virtual machine designed as a portable compilation target. The key phrase here is what I put in bold. It's a portable compilation target. Yeah. What it provides is a lightweight, memory-safe sandbox execution environment, pretty much a container or virtual machine, in which you can run code compiled from any supported language, so C and C++, obviously. Rust has really good support, but Swift also has support for WebAssembly. All you need is a runtime to run the WebAssembly module, but these runtimes are available pretty much anywhere, not just on the web. So that's why I said WebAssembly is a bit misleading. You can compile anything to WebAssembly and run it anywhere that you have a WebAssembly runtime, not just in a browser. So what does WebAssembly enable for Swift developers? Well, obviously, you can run Swift in a browser. Now, that doesn't mean that you can just go home, open up an iOS project, click compile to WebAssembly, and run it in a browser. That won't work, unfortunately. But if you architect your app in such a way that all of your platform-independent code, so all of your domain logic, is separate from all of the platform-dependent code, then you should be able to reuse most of your domain logic to build a web app. A nice example here is GoodNotes. I assume some of you are familiar with GoodNotes. It's a popular note-taking app for iPad. And they used Swift WebAssembly to build a web app. So this web app reuses about 100,000 lines of Swift code to build a web app with a React UI, which is quite impressive. So if you want to see how they did it, why they did it, check out that link. That's a talk they gave last year at NS Spain. So that's the obvious use case, but there are others. You can also use WebAssembly to run Swift on the server. In case you didn't know, we can already run Swift on the server. We even have a separate server-side Swift conference. But WebAssembly still has something that it can offer here. So as I said, it is a lightweight, memory-safe, sandboxed execution environment. So it's kind of similar to Docker containers, but compared to Docker containers, WebAssembly modules have the potential to be a little bit more lightweight and faster to load than a full Docker container. So this makes them really useful, especially for stuff like serverless, where low memory footprint and fast loading times are really important. An example of this is the Swift Cloud platform. This platform lets you write serverless functions in Swift. They compile your Swift WebAssembly and they deploy WebAssembly on Fastly Compute. If you want to learn more, just check out the link. That's a talk from the 2022 Server-Side Swift conference. And then the most recent use case I learned about is that you can use WebAssembly to build a plugin system for your apps. So even if you have no interest whatsoever in web development, you can still use WebAssembly to build plugins and load them into your Swift app. A nice example here is this Google Summer of Code proposal. It describes how we can use WebAssembly to compile Swift macros and then load the compiled macros into our Swift apps. This should really reduce the build times that are associated with using macros. So of course, this only works because we also have a Swift runtime, WebAssembly runtime written in Swift that we can import into our apps, and we can use that to load WebAssembly plugins. So if you want to learn more, check out the link again in the corner. So as I mentioned earlier, all of this is made possible by the SwiftWasm project. I'm not affiliated with them in any way, but I'm happy to stand here promoting the work they've done to support WebAssembly in Swift. So what do they offer? Well, first and foremost, they have a toolchain that adds support for WebAssembly. The upstream Swift toolchain has some support for WebAssembly because most of the changes have been upstreamed already. But if you want full support, you still need to use, for now, the separate SwiftWasm toolchain. SwiftWasm also offers Carton, which is a Swift package manager plugin that makes it really easy, as you'll soon see in the demos, to build web apps with Swift. So if you want to go the web route, you can just use Carton, build and load it in a browser. Of course, if you're going to do any web development, you will have to deal with JavaScript. So SwiftWasm also has JavaScript Kit, which enables both bidirectional interoperability with Swift and JavaScript. And then finally, SwiftWasm also provides WasmKit, which is the runtime I mentioned earlier, implemented in Swift. So you can just add it to your app, and then your app can also load WebAssembly modules. That's my introduction. So I hope you're all excited to see some stuff in action. All the demos I'm about to show you are on GitHub, so you don't have to worry, just follow along. And at the end of the presentation, you can check out the link and just try it all out for yourself. So now I need to mirror my display, which, as I've learned, isn't always that easy. That's an inside joke. All right, first demo. This is a Hello World type demo. I didn't actually make Hello World because it's a bit too trivial. So this is what I consider to be Hello World, which is just rendering something on a web page using Swift. So as I mentioned, the easiest way to do this is to use Carton. So in package.swift, I just declare dependency on Carton, and also on JavaScript Kit, because we're going to be interacting with the DOM, document object model, to get elements, append elements, modify elements. So I just have these two dependencies, otherwise it's just a plain Swift executable package. And then in main.swift, I just get the window.document object, create a paragraph element, set it text, and append it to the body. So we're creating a new paragraph element and appending it to the body element. Now, the way this works is, of course, by using JavaScript Kit, but JavaScript Kit offers a JS object.global object. This corresponds with the window object that you may be familiar with if you've done any web development. And so the window or the global this object. In Swift, this is called JS object.global. And then next, JavaScript Kit relies really heavily on dynamic member lookup. So all of the APIs that you may know from JavaScript, so all of the properties, methods, and so on, they're made available through dynamic member lookup. So in this simple demo, this document property, create element method, this inner text property, this body property, and this append child method, they're all accessed using dynamic member lookup. So just keep in mind, they are all available automatically. You just won't have any static typing or auto-completion and so on. Okay, so how do we compile this? Well, if you're using Carton, you can just call the plugin. So use Swift run Carton. Def is a debug build. You can also bundle to do a release build. And you specify your index.html page. Otherwise, you just get a blank one. And run it. And now Carton is going to do a lot of stuff behind the scenes. The first thing it will do is it will check if you have a Swift-version file. And here you can specify which release of the Swift WASM toolchain that you want to use. So as you can see, I like living dangerously, so I updated yesterday to the latest daily snapshot of the Swift WASM toolchain. If you don't have it installed, Carton will just download it for you, which is easy. Just keep in mind it can be about 2 gigabytes in size, so it's quite a big download. Once the toolchain is installed, Carton will use this toolchain to compile your project. This gives you a WebAssembly module. Then Carton will generate a bunch of JavaScript boilerplate to load the module into your index.html page. Then it will spin up a web server. It will deploy your HTML page with the compiled module and the boilerplate JavaScript, and the result should be here. Ooh, yeah. That's not worthy of applause yet because Carton makes it really easy. But if your goal is to learn about how all of this works, it's a bit too easy. So let me close this demo. So in the next demo, I try to take a step backwards. So I wanted to learn how I can just compile something by hand without the help of Carton. So what if I don't have what if I'm not doing web development? I want to compile something, run it on the server. Or what if I already have a web app? Just look at the goods notes, so they have a React app, and then you want to integrate some Swift modules. So in this demo, I want to see how I can build my package just using Swift without Carton, and then integrate it into an existing normal NPM Webpack web app. So all of the following demos, they have the same structure. There's a Swift package. There's a web app that uses NPM for dependencies, Webpack. And then there's a simple build script to just tie it all together. This just builds the model, copies it into the web app, builds the web app, and runs it. So let's start by looking at main.swift. Again, it's not Hello World. I just wanted to make it a little bit less trivial. So here I have a simple app. It just prints out whatever command line arguments and environment variables that you passed into it. That's it. To build it, the command is here in the build script. You just Swift build. You specify the target triple for WebAssembly architecture and static linking for the standard library. Just keep in mind that if you're building it this way without the help of Carton, just make sure that your Swift executable is from a Swift WASM toolchain. So my $Swift is just a library developer and so on. My toolchain, installed by Carton in the previous example, /user bin Swift. And the normal Swift toolchain doesn't support this specific triple. It has some support for other configurations, but not this specific one. And then the output of this build command is a WASM file, which should be in .build, the triple, and then I did a debug build. And then we should see here a command.wasm file. So that's my WebAssembly module. I didn't use anything web-specific. I'm just printing out stuff using Foundation. So I don't actually need to build a web app to run this. As I mentioned earlier, you can install WebAssembly runtimes pretty much anywhere. So here I have one installed on the command line, which is called wasmer. So I can just wasmer run this module. And then it should print, it was run with no arguments other than the command itself and no environment variables. The nice thing about wasmer is that it also has an inspect subcommand, so you can wasmer inspect the same module. And this is how I learned a lot about WebAssembly, just by inspecting the modules that I compiled. So what you need to understand here is not the actual WebAssembly code. It's also hidden by wasmer inspect. Only that modules export functions and import functions. So your imported functions are your dependencies. Your exported functions are the functionality that you provide as a module. In this case, the module imports or declares dependencies, a bunch of functions prefixed with WASI underscore snapshot underscore preview1. These are the WebAssembly system interface. So WASI stands for WebAssembly System Interface. This is how modules can interact with their host environment. If you know POSIX, it's basically POSIX for WebAssembly. So a more lightweight system interface than POSIX, but specifically for WebAssembly. This also means that when we load the module into web app, we also need to provide an implementation for all of these functions when loading the web app, because these are the functions that the module depends on. Then in the export section, I only have one single export, which is a start function. If you build an executable, you get a start function. It just runs your code in main.swift or your add main function, top to bottom, that's it. So this is the function that we need to call to run the code in main.swift. Okay, so we have a compiled WebAssembly module. We can now load it into a web app, which should be here. So that's all the boilerplate code that I mentioned earlier that's generated by Carton, but it's not too hard to write once you understand it. So in order to load a module, you need a runtime. Specifically, if you're depending on WASI, you need a runtime that supports WASI, the same version as the one that you're using. So in my case, preview1. So here I'm using micro WASI, which is also provided by SwiftWasm. So it's a very small WASI runtime. So I just create a runtime. I set some arguments and environment variables just to check that my app is working, because it wants to print out these arguments and environment variables. And then I can instantiate the module, basically just loading into memory. So when you instantiate a module, of course you specify the module itself, but you must provide a very special object, which is known as the import object. So this object must provide implementations for all of the imports declared by the module. So if the module declares, I depend on WASI underscore snapshot underscore preview1 dot some specific function, you need a property titled WASI underscore snapshot underscore preview1 containing all of these functions. Of course, the actual implementation is provided by the runtime. You just hook it up. But just make sure that the imports are all accounted for here in the import object. So once the module is instantiated, you can run it with runtime.start, which calls the underscore start exported function that you just saw earlier. So if this works, I hope it does, because yeah, I switched to a new version yesterday. Then you should see these command line arguments and this environment variable printed in the console. And here they are. So this is the output of the Swift WebAssembly module. So if you just print, it gets redirected to console.log, and you can see the output here. So that's how you can build a module without the help of Carton and load it into an existing web app. But as you can see, I have a bunch more demos, so obviously this is not the end, because what we did here is we built an executable. Usually that's not what you want. An executable, you can only run it once. You load it, it runs top to bottom, and that's it. Usually what you want is something more like a library. So a library where you declare multiple exports that you can call over and over again. In WebAssembly, this is called a reactor. So a reactor is basically a module that provides a library. Let me run it first so you can see what it does. Then we can check out the code. So very simple example, I have a button, and every time I click the button, it generates a random die roll and switches the image. How does it work? Well, again, we have a Swift app, a web app, and a build script. The Swift app just generates a random number between 1 and 6. Again, it uses JavaScript kit, so it uses the global object. It uses getElementById to find the image object in my HTML page with the image element. And it sets its source attribute and its style attribute. So just generate a random number and set the correct image and make sure that the image is displayed. This depends on JavaScript kit, so we have a bit more work when we want to load it in a web app. But first, let's check out the compiled module. So if I wasm inspect, Swift build, wasm, debug, and it's called reactor.wasm. So if you inspect this and compare it to the previous example, you should see a few differences. First, in the import section, again, you can see all of the WASI functions. But now that we're using JavaScript kit, we also see a bunch of functions declared as imports for JavaScript kit. So we will need to provide an implementation of these in the import object when we load the module. In the export section, we no longer have a start function, we have an initialize function. Start is for executables, initialize is for reactors or modules. We also explicitly export our main function, which doesn't happen by default if you're a library. And we have a bunch more exports that are provided by JavaScript kit. So the SWJS is SwiftJS is JavaScript kit. So JavaScript kit is implemented part in JavaScript, part in Swift, and the two parts are interacting through these imports and exports. So to load this in the web app, few changes. Again, we need a runtime. So that's our WebAssembly WASI runtime. We need an implementation of JavaScript kit that can provide the imports that we just saw. So that's our JavaScript kit runtime, if you want to call it that. And then when you instantiate a module, you provide implementations for a WASI underscore snapshot preview 1 and a JavaScript kit, a JavaScript underscore kit, which was a name that you saw listed here in the imports. So that takes care of all of the imports. Then for reactors, you have to keep in mind that you must call initialize first before you call any other exports. So as you can tell from the name, this initializes the module. So you're required to call it first, once and only once, before you call any other exports. So call initialize first, then connect JavaScript kit, the two parts, the Swift part and the web part. And after that, you're free to call any of the other exports as much as you want. All of these exports are provided through instance.exports. So whatever name you use in Swift, same name is available here through instance.exports. Only main has a special symbol, which is what you see here. So this calls the top-level code in main.swift and runs it. So that's how you build a library. Of course, still have more demos to go, so let's keep going. Why do I have more demos? Because what I just did isn't exactly best practice for libraries. If you have a library, you want to declare multiple functions, export them all, and not just your top-level main.swift code. Usually, a library doesn't even have top-level code. So let's run the next example, see what it does first. So this shows kind of live graph. So there's a Swift WebAssembly module that provides data, and every time the graph wants to plot a new point, it calls into the WebAssembly module, asks what's my next data point, and then just uses JavaScript, a graph and a canvas to render the graph. That's the idea. So the UI is JavaScript. The data comes from a Swift module. So again, I have a reactor or library here, but I no longer have top-level code. I just have one function declaration: get next data point. And then you add two annotations to export this as a function, so you can access it from JavaScript on the other side. So you mark it as expose for WebAssembly, and you specify the name by which you want to call it from JavaScript. Don't forget, this is an easy mistake to make. By default, these functions will use a Swift calling convention, which has extra arguments. If you just want to use these two arguments, so one int in and one int out, specify the C calling convention. So when you declare functions, usually you always have two annotations. One is expose to WebAssembly, and one is use a C calling convention. Okay, so that's enough. If you declare the function this way, then in the web app, you can just access it as instance.exports.getNextDataPoint. It just becomes a function in JavaScript. So that's how you can explicitly export functions in your WebAssembly libraries. It's also nice to notice that if you use the export annotation, you no longer need specific flags here. To build a reactor, you need to specify that you want to link it as a reactor. If you want to export your main functions, if you check out the previous example, you will see there's a bunch of extra flags that you need to pass just to export the main function. If you use expose, you don't need anything else here. You can just expose as many functions as you want. Just make sure that you specify that you want to build it as a reactor. If you leave this out, you get an executable. Okay. So that's exporting functions from Swift into JavaScript. I'm sure you can guess what's my next demo. And the graph keeps on running forever. The next one is doing it the other way around. So what if you have some JavaScript code that you want to call from Swift? I'm not going to run this. It's the same demo as the last one. The implementation is just slightly different. So in main.swift, instead of a get next data point, I now have a plot next data point. So it no longer has a parameter. It no longer returns something. It just plots it directly. Of course, in order to plot this, we need to know what's the current data point, so we can calculate the next one. And I need a function that I can call to plot something. I don't have document object model here. I just need a function that I can call just to plot something. So what we do here is, this is our exported function that we're going to call from JavaScript. It has two dependencies, a current point method and a plot method. These are declared as external functions. So these will be provided by JavaScript. So by annotating it as extern wasm, it becomes an import function, and then we can provide an implementation in our JavaScript import object. So we have graph.currentPoint and graph.plot. So in JavaScript, in our import object, next to WASI, we also add a graph.currentPoint and graph.plot. And the export, again, is available as instance.exports.plotNextDataPoint. So that's how you can import stuff from JavaScript into Swift. So these are my main demos. So you can go the easy route. You can build a web app with Carton and JavaScript kit. Or you can go what I consider to be a more realistic route. If you already have a web app, you can just compile your module, load it into the web app, either as a command or as a library. And you can interact between the two languages with exports and imports. So to finish the demo part, I have one that's a bit more interactive. So if someone has their laptop open, do I see any laptops? People opening their bags. Someone wants to join, go to tinyurl.com/swiftwasm. So I just leave it open for a few seconds. tinyurl.com/swiftwasm. And of course, I need Wi-Fi. Wi-Fi. Yeah, again, not connected yet. And I think it's loading now. Yeah. I hope the Wi-Fi works. Yeah. So it's a simple multiplayer game of Connect 4. So you just enter a username, and then I'm hoping somebody else is already connected. Otherwise, I won't have an opponent. And the demo will be quite boring. Let's see if the server can find me an opponent. Yeah, it can be quite slow to load the first time around. That's also something I'll mention in my conclusions. I did load it this morning, so it should be fine. It works on the phone, but I didn't make it responsive enough to. It's just one canvas that draws the game of Connect 4. Yeah, mine isn't loading. Let's try a different browser.
Mine's saying connecting to server.
Yeah, I'm waiting for mine to load.
So it sounds good.
Yeah, let's try the different one. Of course, this works a million times, except when you do it live. Let's see. Usually I test this by just running 2 browsers and playing it against myself. Then I always win. Yeah. Or sometimes I just give up. Yeah. Do you have an opponent? Hey. Yeah. Hi, Daniel is playing. I am also connecting here. Okay, I'm playing against Davide. Where is Davide? All right. It's my move, so let me pick one first.
Okay, that's it. You can't use the ads.
Okay, voila. Of course, I'm not going to finish. I don't have that much time. But you get the gist of it. So what did I want to do here? Well, I wanted to go back to using Carton and JavaScript Kit. And I wanted to see just how far can I push this. So Carton makes it really easy. You can also load external resources, so you can load your CSS files, images, and so on. So then I tried to build this entire game with only JavaScript Kit for the UI. So the entire UI is also written in Swift using JavaScript Kit and to interact with the DOM. Then the server is written also in Swift, obviously. It uses Vapor and WebSockets. So every client makes a WebSocket connection to the server, and the server just forwards all the moves to the different players who are playing against each other. Another thing I wanted to try is just how much code can I reuse between, let's say, an iOS app, a web app, and the backend. I didn't open this in VS Code, so let's just quickly inspect it. This game is also online on GitHub if you want to see the complete implementation. But the idea is that I built a shared library with platform-independent code. So it has all the game logic for Connect 4, just a single-player game, and then an extra library for all the multiplayer stuff. This is a complete implementation except for the actual WebSocket implementation. So it just has a protocol that says WebSockets can do this, and then you just plug in whatever implementation you have, be it in iOS, in JavaScript, or in the backend. But this shared library is used to build a web front-end, and it's also used in the backend. So you have a single shared library of Swift code that you can reuse and that you can use to build an iOS app, build a web app using WebAssembly, and build your backend if you want to also build your backend in Swift. So that was the idea here. Yeah, the connection is a bit bad, but that's okay. So let's go back to the slides and wrap up. So while you're playing Connect 4, I can wrap up with some lessons learned. So the first thing I learned is that in Connect 4, I tried to write my entire UI in JavaScript kit. Lesson learned, don't do that. JavaScript kit, it relies pretty heavily on dynamic member lookup. So if you're writing code in JavaScript kit, it's like you're just writing JavaScript without the help of your IDE in Swift, with some additional type conversions and so on. So I wouldn't recommend to write your entire UI in JavaScript kit. A more obvious route would be to just reuse as much of your Swift code as you can and build your UI in whatever UI framework that you want to use, be it React or Vue or Angular or whatever. And then you can use JavaScript kit just to glue things together when you need to. Another lesson learned is that cross-compiling is quite tricky. I have an Intel MacBook. I'm compiling for WebAssembly, which is a different architecture. So you have to be really mindful about which toolchain am I using, because I have the one that comes with Xcode. I have an open source one, and then I have the SwiftWasm one. So be mindful about which toolchain are you using, which architecture are you compiling for, and which architecture is SourceKit looking for. Because if you use Carton to compile your app, it was compiled for WebAssembly, but SourceKit in my VS Code is looking for an Intel build. So then you have to build again for your native machine, so all of the auto-completions and error handling will work. Fortunately, we now have Swift SDKs. So if you're unfamiliar with Swift SDKs, you can add support for different target triples to your normal toolchain. So if you use SDKs, you no longer need to download a complete SwiftWasm toolchain. You can just get the SwiftWasm Swift SDK and add support for WebAssembly to your normal Swift toolchain. And SourceKit also supports these, so you can just configure in VS Code for SourceKit that you want to use the SwiftWasm Swift SDK, and then SourceKit is smart enough to know to look for the build for WebAssembly, and don't expect an additional build just for Intel. So it's tricky, but once you get the hang of it, it's doable. Next, and that's also one of the reasons it took a while to load, the binaries can grow quite large. I only did debug builds, so that's also another reason why it's so slow. Release builds obviously are a bit smaller, but for web apps, the binary size can still be quite an issue. I mean, 10, 20 megabytes is already quite a lot just to download the web page. Now, if this is critical for you, I suggest that you also take a look at the work being done on embedded Swift, because they're focusing on really, really tiny binaries. There's also an WASM embedded target that you can use. You don't have support for WASI, but you can get your binaries really, really slow. Kilobytes or even bytes instead of megabytes. And then probably the main issue at the moment is that WebAssembly 1 or WASI Preview 1 is quite limited. Basically, it's all ints in and ints out. There's no strings or higher level types. You can implement workarounds to implement supporting strings, passing strings between JavaScript and Swift, but it involves pointers to shared memory, which is not exactly fun to do. Having said that, I did do it. So there is an example of this in my GitHub repo that shows how you can implement this workaround should you want to get started with WebAssembly right now, and don't wait for version 2. Version 2, I think, has been released, so there's a bunch of big changes coming in WebAssembly 2. Most notably, a component model that has built-in support for higher level types. So that should make things a lot easier. So to conclude, I do want to emphasize I had a lot of fun with WebAssembly. I also was quite amazed about all the things you can do with it, not just building web apps. I was also amazed to see what it can already do, especially like the GoodNotes use case was quite impressive. Swift support isn't as far along as, let's say, Rust or C++, but it's moving fast. It's being upstreamed into the mainline Swift toolchain. So depending on your use case, it may already be production ready. So I would recommend, if this is something that you're interested in, maybe start playing around with it now, and then when WebAssembly 2 support lands, you can delete most of your workarounds and have a much nicer experience. So that's my last slide. If you want to try out any of the demos, scan the code on the left. That's the GitHub repo. I did my best to document them all, so you can just try it out for yourself. You can have all the build scripts. And if you want to support the stuff I do with Swift and education, you can scan the code on the right. So with that, thank you for listening, and if there's time for questions, I will try to answer them.
Thank you, Steven. Yeah, we're already a bit over time, so we will not be doing questions right now. I'm sure there are many questions for this kind of topic.
Yeah, find
It's
me in
good.
the lunch break.
Yeah, it's good that we have almost 2 hours for it. So jump on the Steven's table if you like, not on the table, but like, yeah. Thank you.